This webinar is the first webinar in a series dedicated to net zero emissions to discuss common challenges Canadians face with meeting this target and how collaboration and especially innovation can get us closer to achieving it while maintaining Canada's economic prosperity. To inform our students and members of other organizations who may not be familiar with our organization, the Academy is the national institution through which Canada's most distinguished and experienced engineers provide strategic advice on matters of critical importance to Canada. The Academy is an independent, self-governing, and not-for-profit organization established in 1987 and is one of the 3 nations academies that make up the Council of Canadian Academies. We have over 800 fellows from across Canada, all of whom have made significant contributions to engineering in Canada in the private and public and academic sectors. I invite you all to participate in the Academy and help to achieve the important net zero initiatives by sharing your knowledge and expertise, as meeting the goal of net zero requires massive collaboration. As a matter of fact, global collaboration. I should also mention that the views and opinions being expressed here are those of the speakers and myself and do not necessarily reflect the official policy or position of the Academy. Before we get started, I would like to go over a few housekeeping items and explain the format for our online proceedings. As you have already noticed, you are muted. If you have a question, I invite you to use the Q&A option. It's at the bottom right of your screen. If you see a question posed by another participant that you like, you may upvote the question in order to move it up in the queue. During the general Q&A period, if you wish to be heard, please click the raise hand button, which is actually can be found next to the Q&A. You will then have to unmute yourself once permission to speak is granted by the host. For your information, this session is being recorded and will be available on our website. So now about the format. After my remarks, our distinguished speakers will make their presentations. Following each presentation, I will open the floor to answer a few questions from the audience. After answering the questions for the second presentation, we will have a panel discussion to answer your questions for both speakers. Finally, I will ask each panelist to provide their concluding remarks in 1 minute. The objective of this webinar today is to both set the tone of the continuing net zero webinar series and to discuss the history of climate change agreements, examine the strategies to limit the temperature increase to 1.5 degrees centigrade, survey technologies that are being promoted globally, and hear an overview of Trottier Energy Future projects. We also plan to assess the mitigation pathways in terms of their coherency and their potential of achieving the desired net zero emissions by 2050. Now let's start with my own remarks. The challenge of achieving net zero has been compared to the moonshot project. Perhaps our young audience may not be familiar with the term moonshot, which derives from Apollo 11 spaceflight project and is considered a project or proposal that addresses a huge problem, proposes a radical solution, and uses breakthrough technologies. Like the Moonshot project, the net zero challenge is more of an engineering challenge than a scientific one, requiring massive collaboration. Unlike the Moonshot Project, the Net Zero Challenge directly affects us all. Canada has a wealth of diverse, world-class resources, from hydrocarbon to hydrate and hydrogen, to nuclear, ocean, solar, wind, and more. Canada is also blessed with world-renowned, creative, innovative, inventive, intelligent, and gifted engineers and scientists. The combination of the natural and human resources is next to none. Canadians can lead the world in using innovation and new technologies to find economic solutions to convert our world-class resources to energy and value-added products with minimum greenhouse gas emissions. Thus, this would pave the way to net zero while maintaining economic prosperity for all. This could mean finding breakthrough technologies to convert hydrocarbon to energy without combustion, overcoming the variability and uncertainty by solving the storage challenge for wind and solar energy, commercializing high-temperature gas reactors to ensure power plant safety, protecting nuclear reactors from natural disasters, while finding solutions to manage waste radioactive material, harnessing ocean energy by inventing power conversion devices and cable that convert power to the mainland, and overcoming the hydrogen storage challenge. Unlike the Moonshot Project, which had resources mainly provided by the federal government, it was the US government that provided, and of course, academic and research centers helped, the Net Zero Initiative requires significant commitment and collaboration from various industry sectors, all government levels, regulatory bodies, academia, research centers, technology providers, small and medium-sized enterprises, and public at large. I'm hoping through this series of dedicated webinars to net zero emissions, we can get you engaged, connect ideas, people, projects, capital, and make a small contribution to achieving net zero. On that note, it is my pleasure and privilege to introduce our first distinguished speaker. Dr. Eddy Isaac is the former COE of Alberta Innovates Energy and Environment Solutions and currently an executive fellow of the School of Public Policy at the University of Calgary. He also serves as past president of the Canadian Academy of Engineering. Eddy holds a PhD from University of Alberta and a BSc from McGill University. In my opinion, Eddy is uniquely positioned to talk about reducing greenhouse gas emissions. His paper on the subject is the best, informative, well-balanced, realistic paper I ever read on the greenhouse gas emissions. So please join me in welcoming Eddy. Eddy, you have the floor.
Sohail, thank you very much for this very kind introduction. I wanted to provide, and we're calling it Net Zero webinar number 1, simply because we intend to have a series of webinars, as Sohail mentioned. And mine is a big picture, high level, if you like, overview of what I think is the what should be the content of a net zero emissions from both an international and a Canadian perspective. And then Oskar, who will come after me, will get more into the modeling and the nitty-gritty of what's going to be required and what are the issues that we need to look at. My first slide will be looking at the international efforts to deal with climate change. And it's a historical overview, but also looks at it from the Canadian perspective. So in 1988, very early on in the debate about climate change, the International Panel on Climate Change came into existence, so-called the IPCC. This is the 800 scientists, or maybe even more than that, who were asked by the international community to assess scientific, technical, socioeconomic information relevant in understanding human-induced climate change. Their focus was on human-induced, not all of climate change, but human-induced climate change. And they came up with a series of assessment reports starting in 1990, and the 5th assessment report was completed in 2014. The 6th report is going to be finalized in 2022, and this is the panel of experts that we all depend on for their expertise in telling us the rate at which human-induced climate change is proceeding and how much of it is humanity's responsibility and accountability. In 1982, we had the Rio Earth Summit. The United Nations Framework Convention on Climate Change came into being. It was ratified by 197 parties. And in 1992, already they recognized that stabilizing greenhouse gas emissions in the atmosphere at a level that would prevent dangerous atmospheric interference into the climate system was going to be very important. At the Rio Summit, Canada committed to remain at 1990 levels. Then we had the Kyoto Accord in 1997, which was ratified in 2002 and confirmed in 2005. Canada formally withdrew from the Kyoto Accord in 2011. I think it was the only country to do that. I may be mistaken, but that's to best of my recollection. They're the only country that actually withdrew from the Kyoto Accord. Then we had the Copenhagen Climate Conference in 2009, where Canada committed to be 17% below 2005 levels by 2020. And of course, there was the COP21 in Paris, 2015, where Canada committed to being 30% below 2005 by 2030. And that was supposed to be the lowest level that they wanted to achieve. They wanted to do better than that. They kept saying, governments kept saying, we need to do better than the 30%. And we will be looking at how well Canada has done relative to these commitments. I mention here the IPCC, the International Panel of Climate Change Special Report in 2018. This was an outcome of the Paris 2015 Accord, where the international community, countries, asked the IPCC, give us a report that tell us what should we do, what can we do to limit the increase to 2015. And the IPCC produced this special report, which I will be talking about in the next few slides, of how could the world limit, they looked at a number of scenarios, limit the increase to 1.5 degrees Celsius. And then just as we've been talking about, many countries and many industries have started to commit to net zero by 2050. And this has been happening in the last 2 or 3 years. In fact, net zero has become the rallying cry as more countries and more companies commit to a net zero target. The international community sees this as a solution to the climate crisis, and we'll review that as we go along. I wanted to just remind you of the essential elements of the Paris agreements. There were four main targets: holding the increase in the global temperature below 20 degrees centigrade, and pursuing efforts to mitigate to a temperature increase, to limit the increase to 1.5 degrees C. The second element was that countries must demonstrate increasing ambitions, and many countries push each other to do that. There are supposed to be 5-year reviews as well. Also, increasing the capacity to adapt to the existing impact of climate change is another important target. And then mobilizing funds from developed countries to support the mitigation and adaptation in developing countries. This is how the Paris Agreement is supposed to work. Obviously, this is a cartoon produced by Shell right after the agreement and in the scenarios that they had. You can see here that at some point after 2020, with COVID, maybe the emissions have already peaked, but we don't know that yet. At some point, after 2020 onwards, we have a peaking of emission. We have a point where we have still positive emissions, declining, but still positive. And some point down the road, they would be net zero emissions. Let's say this would be 2050. But very important here is that we also need so the so-called negative emissions or emission sinks to reduce the emissions that are going into the atmosphere. So actually to take them back away from the atmosphere. So just a definition of net zero emissions that I'll be referring to. Net zero emission refers to achieving an overall balance in greenhouse gas emission produced and greenhouse gas emission taken out of the atmosphere. And some other people will call it carbon neutral or climate neutral, they're equivalent terms. How to achieve this? It is to reduce human-caused emission, for example, from fossil fuel use, to as close to zero as possible. And the remaining greenhouse gas emissions that are above zero, if you like, would be balanced with an equivalent amount of emissions being removed, such as by forestry management, through planting trees and doing other things with forest products, through carbon capture and storage, CCS, direct air capture and storage, and also offsets. These are the countries that have committed to net zero targets. So Suriname and Bhutan claim that they have achieved, and the international community thinks that they've achieved net zero. Other countries, Sweden, UK, France, Denmark, New Zealand, and Hungary, have put it into law. Their commitment is part of a law that says we will achieve at a certain date, most of them 2050, those targets. And then there is a host of other countries, including Canada, that have proposed legislation. And this is as of December of 2020, so very recently. There was other countries that I haven't put on this list that are considering net zero emission targets and proposed legislation, but they haven't actually put that into the legislation. So presumably those that are proposing legislation will eventually follow the countries that have put it into law. In many cases, a number of countries have said they want to phase out fossil fuel vehicles. And you can see, I've given an example on the left-hand side, 3 countries and the way they're thinking about it. So Norway wants to ban internal combustion engines already by 2025. They have a strong case because as of 2020, their market shares of electric vehicles have surpassed the 50% mark. In other words, more people are buying electrical vehicles than they are internal combustion engine. A lot of that has been through the fact that they have free charging stations and also subsidize the purchase of electric vehicles. So this is very important. And of course, Norway has a lot of hydro, and that makes it fairly clean energy for electricity. The UK initially said that they wanted to ban the sale of petrol and diesel cars by 2040. That they have now changed their mind and said, no, we got to do this earlier. And so they're saying that it'll be 2035 that they'll ban it, and it's in law. But they also want to make sure that they would be, so if you buy a car, an internal combustion engine car in 2034, let's say, you have 16 years that you can drive it, and then it's got to be off the road. So they're saying by 2050, there will be no gas emitting vehicles. Iceland is a very interesting case because they are so much dependent on geothermal energy. They have a lot of geothermal energy resources. And it's part of their climate change goal of reducing CO2 emission by half by 2030. And like the UK, they want to abolish gas-powered vehicles by 2050. They've also been doing exceptional technologies. They've been looking at exceptionally good technologies, both for hydrogen use. They have the first system of hydrogen vehicles, as well as using sequestration. This is in basaltic rock in the geothermal area, where they inject CO2 and it becomes a rock as part of the geothermal. So a lot of very interesting things happening in Iceland. On the right-hand side, and I'm not going to go through this, but just to tell you, there are other countries with plans to disallow gasoline vehicles, and most of them talk about 2050 being the date to do that. I mentioned the IPCC special report that they were commissioned, the scientists were commissioned to model and limit the increase to 1.5 degrees Celsius. They had to do a number of scenarios because they didn't know what the energy demand was going to be in 2050. So the first thing they assumed is that we're going to have behavioral change. We're going to have to be much more efficient. We're going to conserve energy. And that was the 32% scenario. And then they said, well, maybe we don't do that so well. So that's the -5% scenario. So these are all negative scenario. In other words, we're conserving energy. But population growth may take place and so on. So you have scenario 3 and 4, which means that you have an increase in energy demand. In order to preserve the 1.5 degrees, though, you had to limit the emissions that's relative to 2010 by over 90% in all scenarios. So from 91 to 97% in all scenarios had to be limited. That means practically many of the fossil fuels that we're used to doing things would have to be eliminated or shut down. So now they had to say, well, what do we do now to compensate for the fact that we are using energy that is not fossil fuel based or less fossil fuel based energy, almost to very low levels. And so this is what comes out, that you had to increase nuclear from what it is today. You'll see that in one of my other slides, from 100% to 500% to do that. And renewable, this is solar and wind primarily, but also hydro and geothermal and so on, would have to increase by 830% to 1140. So 8 times and 11 times increase. Biomass, depending on the scenario, would either go down a little bit or be increased by 4 times. And the renewable share in electricity would have to go from what it is today, and you'll see what that is in a few slides, to about 70 to 80% of the entire electricity picture. And the most interesting is they talk about cumulative carbon capture and storage. And I've combined the number on carbon capture and storage with bioenergy with carbon capture and storage. That is, the bioenergy with carbon capture and storage is actually a negative. You burn trees that have been grown, but you also capture the CO2 from these trees. And here we're talking about 350 to 1190 gigatons of CO2 during the period from now till 2100. And if just to tell you that the entire global economy uses 40 gigatons of CO2 per year, you can see that these are very large numbers. And you have to do all of that in combination to make up for the shortage of fossil fuels that you have reduced. So this is a very, very difficult task indeed. And Sohail mentioned this. I did write a paper on this very subject, which I called Climate Change Solutions, Sensible or Misguided. And it focused on the climate agreement. And you can certainly download this from the internet for your interest. Many countries have climate change plans. And you look at the climate change plans of a number of countries, especially in the Western world, which is designed to limit the increase to 1.5 degrees centigrade. You see very common objectives or very common policy things that they do. The first thing and most important, I think, is conservation and energy efficiency. And many countries believe that they can reduce their emissions through behavioral change, energy efficiency, and conservation by 20 to 30%. So it is a very significant number. A number of countries have wind and solar targets and want to switch to more renewable energy. In fact, the whole world is in that position. Biomass for heat and power, I put a question mark on that, but that's also fuel switching from fossil fuels to using biomass, and you'll see why I question this as a strategy. And then transport, building, and industrial electrification, a lot of talk about we need to electrify all of the services that we provide. And so biofuels, another question mark on my part. And nuclear and hydrogen, because I'm going to touch on these. I thought I would highlight them, but also you have hydro, tidal, geothermal, and other sources of low carbon energy. But I will focus on nuclear and hydrogen. And then, of course, countries that have fossil fuel production are working very hard. Canada is certainly in the forefront of that in reducing the energy intensity of their resource, their fossil fuel resource. Countries that do not have fossil fuels are urging other countries that do to leave the fossil fuels in the ground. And there's been a number of academic studies that have said who should go first and who should leave their fossil fuels in the ground. And you can imagine that Canada comes to the top of that list. And of course, there's carbon capture and geological storage. My colleague Oskar is going to talk about this in the context of his presentation. And you have negative emissions, forestation, forest products, increasing soil carbon, bioenergy with carbon and capture and storage that we spoke about, and direct air capture. A number of these, I think, are good solutions, especially forestation. But things like direct air capture is something that I believe is not going to make it on an engineering scale that is going to be required. Nevertheless, these are negative emission targets.
Eddy, you asked me to let you know about the 20-minute timeline,
Sure.
So we got there. Thanks.
All right, thank you. So fossil fuels still supply 80% of the world energy. So I just wanted to say that even though we've made a lot of progress, it's been very slow. COVID may be different. Renewable energy in the 28 EU countries in 2015, I couldn't find any more recent numbers, and the IPCC guidelines to that. And you can see that in the EU countries, what they call renewable energy has mostly, or at least 65%, over 60% biomass and waste co-firing. The IPCC's guidelines say that emission going to the atmosphere are net zero and are not counted. They count the emission from harvesting, land use changes, use of fertilizers, and so on, but that's only accounts for 30% of the emissions, and emissions from burning the biofuels are just not counted under the IPCC guidelines. They're counted as zero. But it seems that declaration that biofuels are carbon neutral has allowed EU countries to increase their emissions. This has turned out to be a bad assumption because it turns out that wood emits more CO2 than the fossil fuel per unit of energy released. And a study that was done showed that because the emission of the CO2 in the atmosphere is and you have articles every now and then in the Guardian. This is an article in the Guardian that talks about the carbon neutrality is a fairy tale and how the race for renewable is burning European forests. And this is the use of wood pellets as an alternative to coal. And as you know, Canada supplies many of these wood pellets. So does the US to European countries. And there have been subsidies in biomass energy in EU, and that has caused a certain degree of increase that you can see here in both the consumption in the EU of biomass, as well as more than tripling its consumptions in the UK. I'm just going to highlight the nuclear area, and I'm going to skip the hydrogen area if that's all right, and then we'll go to a summary and conclusion, if that's all right, Sohail. There are 440 nuclear power reactors operating in 32 countries. In China, you have 0 operating nuclear plants in 1990. But by 2019, they had 46 nuclear plants in operation and 11 under construction. What a phenomenal increase in that country. On the other hand, in the rest of the world, we've had 186 nuclear reactors shut down permanently, most of them replaced by natural gas. Germany talks about shutting all its nuclear plants by 2022. Whether that happens or not remains to be seen. In France, electricity is 75% from nuclear energy, but no new plants have been built over 20 years. And the government policy is to reduce their share of nuclear to 50% by 2035. Again, decline in nuclear use, and we see that in the global picture as well. And this is the last nuclear plant built in Canada, the Darlington plant. It was scheduled, it's 5 years over the schedule period and 3 times more than the estimate that was received. And this is very typical of what's happened to nuclear energy. There's a very number of examples in Georgia. The nuclear plant that's being built is also quite a bit over budget. The one in Finland that Arriva is building is also over budget. And I bring it here to demonstrate that one of the things that we've lost is this capability of doing things on budget. And my colleague Oskar is going to talk about that as well. And just to say that this picture is from an old study done by MIT looking at what is possible in the future and what will be available. That's small modular reactors, advanced fission, and fusion reactors, which will be possible. I think their availability is a little bit overstated. I think it's going to be later than that they've stated here, but certainly a pebble bed reactor is already in operations in China. I don't know what the status is and how it's operating, but it's certainly in commercial demonstration operation. So hope for nuclear comes from small modular reactors, advanced fission, and down the road in the future from fusion. As I mentioned, I'll skip the hydrogen and just mention that in all of the attempts for Canada to meet its targets that they've set, they have failed quite significantly. Their actual emissions have remained pretty much above 700 megatons of CO2 equivalent. Rio is supposed to be at 600, Kyoto at this level, Copenhagen 17% below 2005 targets, and Paris below 30% target. So what we do have now, and I'll make this my last slide, Sohail, is that Canada's net zero emission accountability act has come into being. There is a determination by the Canadian government to stay the course of trying to achieve the net zero target. They are intent on doing that by law, like some of the other countries we've seen. This is going through Parliament to do that. They've set 5-year milestones for interim emission reduction targets. This is very much like the UK has done. They've also have a climate plan called A Healthy Environment and a Healthy Economy, very much the theme of this seminar, in which the carbon price is to reach $170 per ton of CO2 2030 They've added 1.5 billion to increase the production and use of low carbon fuels. By that, I think they mean biofuels and things like hydrogen. They've added 275 million to the pot that already existed for incentives for zero emission vehicles, and added 150 million in vehicle charging and refueling stations, again, trying to move the country into more electric vehicles. And of course, there is a federal clean fuel regulation that requires fossil fuel suppliers to reduce their carbon emissions by 13% by 2030, and from 2016 levels. And there's more to come. So I'll stop here and turn it over back to you, Sohail. Thank you.
Eddy, thank you very much for extremely informative and thought-provoking presentations. I really enjoyed it. Just a couple of questions. One questions from the audience. They are wondering about this concept of a green label on meat as a way to kind of provide a solution. What are your thoughts on that?
You know, there has been a study done by the UNDP, which came out a couple of days ago. It was done through Oxford University, in which when people around the globe were asked about what they thought were the best policies, many of them went to forestation, going to renewable and so on, switching to plant-based diets was the lowest, from a global perspective, was the lowest priority that people put on things. So I'm not sure it's going to be very helpful to do that. I think that people have to, on their own, take the bull by the horn, and if they really are serious about reducing their dietary requirements of meat and moving more to a vegetarian diet, it doesn't have to be exclusively vegetarian, then it's a behavioral change that has to come. But I don't think globally people are ready for it.
I'm sure that my family are not ready for it. I know that. So the next question is, overall, do you think this net zero is achievable? Is this practical by 2050 or even maybe later on? What are your thoughts?
Well, you know, I wanted to have the title a net zero climate change solution or net zero delusion. A climate change delusion. I think that it's really great that countries are so much committed to doing the right thing. But you know, we've gone too far in our emissions into the atmosphere to change that dramatically over the next year. So all we can do is make it less worse. It's going to get worse. The question is, how much worse is it going to get from a climate change point of view? So I have two minds. I think it's great that people are, and countries and industry wants to do this, but I think the technologies that need to be employed to do it are, you know, very, very difficult. You know, so it's difficult for me to believe that we're all of a sudden going to fossil fuels are going to disappear, and we're going to be using all kinds of other energy when it's difficult to do that.
Sure. Well, there are 8 more questions, Eddy, but I think maybe we can postpone it to have pose it at the when we open the panel discussion. But just one quick question also, Eddy. They are asking whether you would be willing to share your PowerPoint presentation with the audience.
Oh, definitely.
Okay, thank you very much.
This will be on our website, I imagine.
Oh, absolutely. I mean,
yeah. So they can, the people can certainly go to our website and download it. I would suggest that's the way to do it.
Yeah, no, it was great presentation, really beautifully done. So thank you very much. And now I would like to introduce Dr. Oskar Sigvaldason. Oskar worked with ARC International, a global consulting engineering company, for 38 years. 9 years of it, actually, he served as president. His work included engineering and project management for major power projects. More recently, he served as project manager for the Trachea Energy Futures project. Oskar is a director and also former chair of the Energy Council of Canada, and also a former member of World Energy Council Studies Committee. He completed his undergraduate and postgraduate studies in civil engineering at University of Manitoba and at Imperial College, University of London, respectively. His doctoral studies was completed at Harvard University. He is a fellow of the Canadian Academy of Engineering, Canadian Society of Civil Engineers, and International Water Resources Association. He is a life member of the Energy Council of Canada. Oskar has done an outstanding job evaluating different paths in achieving net zero. So please join me in welcoming Oskar. Oskar, you have the floor.
Well, thank you very much, Sohail, and good morning or good afternoon to all of the attendees to this webinar. It's very gratifying to have such a huge turnout, and we just hope that we will meet the expectations of this first of a series of webinars. So my presentation is really a follow-up to Eddy's. I will be talking very briefly about a study that the Academy of Engineering was involved with. It's the Trachea Energy Futures project. I will also talk about some of the challenges in certain sectors. These are engineering and management challenges. And then at the end, I will try to emphasize the importance of integrating scientific and engineering activities on the various challenges that are associated with achieving net zero, with the importance of having comprehensive, integrated, fact-based planning. So that's the essence of what I want to cover. I'll go through this fairly quickly so we have time for lots of discussion. So on to the next slide. So the Trachea Energy Futures project is an example of Canadian expertise for integrating economic planning with GHG mitigation and transformation of energy systems. Next slide. So this is a study that was funded by the Trachea Family Foundation, committed in 2010. It's carried out during the period of 2013 to 2016, and results in a report which is titled Canada's Challenge and Opportunities, which was submitted at the Trachea Energy Institute at the University of Montreal in 2016, which is now 5 years ago. But the goal of the study was to assess options and pathways for reducing GHG emissions by 80% by 2050 relative to 1990. So that was the prevailing thinking at the time of this study. Next slide. As noted, it was funded by the Trachea Foundation, and it was co-sponsored by the Canadian Academy of Engineering and the David Suzuki Foundation. And the idea was to have two national organizations that came at this challenge, the climate change challenge, from very different perspective. The Academy is well known for being very scientific and fact-based, and the David Suzuki Foundation looks at this in a little more abstract way. So the notion was that if we could get these two organizations to really agree on what a plan should look like for all of Canada, then this would be an accomplishment. And we achieved that. So I will just run through, I will not go through this in detail, but I'll just run through this quickly so you have an essence of what a planning study that combines economic growth, GHG mitigation, and transformation of energy systems looks like. Next slide. So the approach for the study was, first of all, to assemble a very strong multidisciplinary team from across Canada that covered all of the sectors that needed to be reflected in the overall study. So we had a team of about 12 people, plus extensive peer review. We used two mathematical models, an optimization model and simulation model. The optimization model is referred to at the times Markel model, which was initially developed for the International Energy Agency, or actually for the U.S. Department of Energy, but was then transferred to the International Energy Agency. And that was developed, the initial version that was developed in the late 1970s, so it's been around for a long time. But there are variations of this model that are being used in 70 different countries. So the only one that exists in Canada is the one that's held by Esmia Consultants in Montreal, Kathleen Biancourt, who is very closely associated with the University of Montreal. Given that this was the first time that we had used two models, it was very important that all of the data that went into the model. So we spent actually the first 6 months really focusing on the information that went into the model. So it was extensively peer reviewed. We had 14 working papers, expert review panel appointed for the study. And then we had external review, which was carried out by the Canadian Electricity Association on the electricity sector and by the Canadian Association of Petroleum Producers on petrochemicals. 11 scenarios, and the basic goal was to maximize present worth economic value for all of Canada and its 13 provinces and territories for the cumulative period, for the 40-year period, to meet increasing demands and GHG mitigation targets. So next slide, please. So the special considerations, first of all, we were looking at growing demands with the increasing population. We did a population projection which showed the population growing from 35 million in around 2010 to 48 million by 2050. The GDP per capita growing from 45,000 per capita to 65,000 per capita. This was all in terms of constant 2011 dollars. And then industrial output growing to meet the growing demand. Given that this was the first time that formal optimization methodology had been used to derive the net economic value over the cumulative period, we felt it was important to start with a no constraints premise. So we wanted to say, what is the absolute ultimate potential for Canada to maximize its economic growth? So we eliminated regulatory constraints, environmental constraints, other than sensible things that were already there, into jurisdictional constraints and so on. So it was just to get that big picture. We also recognize that long-term planning is a three-phase process where you begin with defining pathways. How do you get from here to 2050 in the best possible way? And then that would serve as a basis. So we would have alternative pathways which would serve as a basis for discussion by government leaders, by political leaders, and by business leaders, and by the environmental community and other stakeholders. But then pathways would lead to strategies, and strategies would lead to policies. So the focus of our work, given that this was really the first time, was really more on defining pathways. We had special considerations, such as dispatch constraints, and dependable capacity with intermittent renewables, and I'll come back to that later. We had to address differential cost and transmission grids depending on the amount of wind and solar, which would all need to be backed up with other sources of dependable capacity. We included grid storage and then changing costs over time, particularly with solar and wind coming down quite dramatically over the projected 40-year period. Next slide. So this is just a quick overview of what is a composition of emissions in Canada. This was in 1990. And from this, first of all, the emissions really break down into combustion emissions and non-combustion emissions. So the non-combustion emissions are shown on the right-hand side and includes industrial process emissions. These are emissions that are basically occur from chemical processes in refineries and different industrial sectors. The agricultural processes, which is primarily methane and nitrous oxide. Then there's emissions from waste, primarily dominantly from landfill municipal sites, and that's primarily methane. And then the fugitive emissions, which is really emissions that are associated with leakage in the hydrocarbon sector, but are not associated with combustion. So on the combustion side, we have roughly 50% is in end uses as shown here, transport. This is on the lower left side. And then on the upper, at the top, we have the emissions on the supply side, which is electricity and fossil fuel production. It's important to note here that the electricity was primarily the burning of fossil fuels for the production of electricity, and the fossil fuel production included the whole supply chain for both meeting end uses as well as for export. So that's the breakdown. So the non-combustion emissions is about just over 25%, with between 26 and 28%. So next slide. So the modeling that we did, and we did this with both models, we represented Canada by its 13 provinces and territories. Next slide. We represented the entire energy network from primary resources at the left-hand side to demand for energy services on the right-hand side. I'm not going to go through this in detail, but the model really was driven by demand for energy services. And then that, the whole solution process then selected the optimal combination of primary energy sources and transformation processes as we go from primary energy to meeting end uses. Next slide. We did 11 scenarios. Basically, in each case, we needed to have a reference scenario, which was, we sometimes called it the do-nothing scenario, but it was really a scenario that said, let's pretend that there's not a climate change problem. Okay, so what would the solution look like? So that was always the reference scenario, and then all the other scenarios were always in relation to the reference scenario. So these scenarios basically went from using existing technologies dominantly to increasingly using additional, what we call like second and third generation biofuels. We looked at changes in urban form. We added carbon capture and storage. We didn't have that at the beginning. We looked at one scenario in which we said, what does the solution look like if there's no more nuclear ever built in Canada? And we also looked at including the BECCS solution. This is the bioenergy that Eddy had referred to, which was using wood waste, or basically using bioenergy, which would be wood pellets primarily, for generating electricity and then capturing the CO2 and storing it, sequestering it. So next slide. So this was one of the major drivers in the modeling approach. The S1 was the one in which we pretended that we were going to ignore climate change. So that was the reference scenario. And then we had a series of runs which were based on variations from 30% reduction relative to 2011 to up to 60% reduction of 2011. We had difficulty in this study going much beyond 60% reduction because the solutions, particularly for heavy freight transport, were very problematic. Now we know that in the development since then that it's now much easier to get to 80% reduction. But at that time, based on the knowledge of available technologies, we had real challenges in terms of getting much beyond 60% reduction. Next slide. So this slide very quickly just shows what happens with the reference scenario. So we have the emissions growing from 600 million tons to 1,100 million tons, not quite doubling. I should note here that in the economic projections, we saw the economy growing by a little over 100%. So the demand would not be as rapid as the growth in economic, overall growth in economic demand. Next slide. So we did, these are a series of slides. We had this for each of the 11 runs and for variants of the 11 runs. So we had a very large number of these kinds of slides. But the top diagram basically shows where we would have reductions in the various sectors. Because the top slide is the do nothing, and then the dotted line boundary is associated with the GHG emissions constraint. So again, not going into this in detail, but this was very helpful in demonstrating that the minimum cost solution resulted in rapid decarbonizing of electricity supply and early attention to decarbonizing the transportation sector, especially for cars and light-duty vehicles. So this is just an example of the kind of output. Next slide. This is another key slide that showed a couple of really important things that came out of the study. First of all, even with the economy growing and trying to meet some of the GHG emission targets, the overall demand for electricity, for energy, which is in petajoules, around 8,000 petajoules per annum. That if you ignored climate change, then you had this increase in overall energy demand. But when you put in the restrictions, the demand for energy actually did not increase. So it remained relatively constant. This was very robust for the various scenarios. So that was one observation. So you had a situation where the economy was doubling, but the demand for energy was constant. The second observation is and this is a very significant one, is that the mix of the energy to meet end uses changed dramatically. For the current scenario, about 74% of end uses are provided by hydrocarbons and derivatives, gasoline and diesel fuel primarily. And that, when we go into the solutions here, that comes down dramatically from around 70% to around 25%. And electricity, on the other hand, then makes up for this reduction in use of fossil fuels to meet end uses. So the role of electricity, which currently is about 22% of end uses, rises to up to 60%. And in more recent studies, it rises even further than that. So that is the most dramatic change that came out of this study. This is switch from the use of hydrocarbons for end uses to the use of electricity for end uses. There was also an increase in biomass and biofuels. So next slide. This is just a slide that shows the marginal cost, which is roughly equivalent to the carbon price. So we were looking at numbers which were in the hundreds of dollars per ton. So the legislation is being proposed, getting up to $170 per ton, is better aligned with the results that we showed here. So it's just to bring out that the marginal cost of GHG mitigation is in the hundreds of dollars per ton, not tens of dollars per ton. Next slide. So the principal observations, first of all, is the dominant source of combustion emissions is to meet end uses. This was counterintuitive, but basically says that when you burn gasoline in your car, and you look at the entire supply chain from when it's when the oil is taken out of the ground in Alberta or British Columbia, transported across Canada to the end uses, the emissions from that whole supply chain to get it to your gas station represents 15%. 85% is when you actually combust it for motive power to drive your car or pickup truck or whatever. And the same is true when you use natural gas for heating homes. So the dominant, so this is really, if we're going to make changes, it has to begin with the transformation of end users because it's the dominant one, beginning with the transportation sector as being the most important. So as Eddy has pointed out, energy conservation, energy efficiency, and I've already covered the dramatic changes for meeting in the mix for meeting end users. Generating capacity now, we're looking at tripling the capacity from 135,000 megawatts at the present time to more than 500,000 megawatts. And that's variable depending on the amount of intermittent renewables because it all has to be backed up. The electricity supply and transportation are the early priorities, and there's a lot of investment in high voltage interconnections. And the sink, which again Eddy referred to as becomes a very important part of the overall strategy because it's not just reducing emissions, it's also increasing the ability to sequester the CO2 in one form or another. Next slide. So I just wanted to come on to 5 examples of where there are very significant engineering technologic challenges. The first I just wanted to mention is grid scale electricity supply. We're looking at a 3-fold increase in electricity to meet the transformation of end uses. These are the challenges. You have a huge increase in infrastructure. You have to decarbonize what already exists. You have to replace, because a lot of the electricity infrastructure is already old. You have massive investments in interconnections, and grid scale storage becomes important. So when you look at the strategies, even though we are talking about intermittent renewables, which I'll cover in the next slide, the bulk supply is still going to be dominated by hydro, nuclear, and thermal. Those are your 3 sources. Sorry, just go back a slide, please. Yeah. So, I mean, there are others that come into play, but these are the main ones. Hydro is, of course, dominant in Canada, but worldwide, thermal generation represents 67% of total electricity supply. And with hydro being a limited resource and nuclear having its own share of challenges, then thermal is likely to continue to be a major source of generation. However, and this would be dominated by natural gas, however, thermal will require carbon capture and storage, sequestration. So the work that has already been done in Canada on both the, particularly in the Boundary Dam project in Saskatchewan, which has served to demonstrate the viability of thermal generation with carbon capture and storage, and the Quest project by Shell in Alberta. These are very significant developments because they serve to attest that this is really a viable option. When we did our study, we were not there. Hydro is very important, but what we need to be looking at is adding capacity at existing sites in addition to new hydro sites. Interconnections I've mentioned and large-scale grid storage. The next slide. The second one I have here is low-cost wind and solar. I mean, this is a very attractive option because it's low cost, quick and easy to install, and at the present time, it has great public support. But the challenges with the low-cost wind and solar is that it does not contribute to dependable capacity. This is the capacity that is required to guarantee availability at peak demand periods. And it also has highly variable output, which requires very fast response, compensating supply. So the strategies, first of all, wind and solar, because of its cost competitive, should be maximized. But there are system integration limits, which are very dependent on the composition of the rest of the supply system. But generally, it's very difficult to see for Canada that this is going to be more than 20% of electricity supply. There's really an outstandingly good study that has just been completed by the Academy was very much involved in that, but it was the International Council of Academies of Engineering and Technological Sciences, which is CAT. This was a study carried out by cooperation by 21 countries, in which it was demonstrated that the dominant issue or dominant challenge with low-cost wind and solar is the management of intermittency. And there are some recommendations in that report, but the key thing is that you have to have a system which can compensate for basically large instantaneous changes in electricity supply from wind and solar. So it's sometimes some people refer to this as a detail, but it's a very important detail and so on. And that is the ultimate limiting driver on the amount of wind and solar you can install in different systems in Canada. Next slide. I wanted to bring out the engineering and project delivery for large-scale power projects. Canada has the lowest cost electricity supply in the G7, and it has benefited greatly from past investments in major projects, hydro, nuclear, thermal. So we're living off that. However, currently there are major cost overruns, and Eddy referred to that, with large projects, primarily hydro and nuclear, and not just this is worldwide. And there's clearly a lack of public confidence in managing delivery of large projects. There's a perception that large projects just have massive overruns and massive schedule delays. What is interesting is that 50 years ago, this was not the case. So the expertise that existed at that time for the delivery of large-scale projects, which was really exceptionally good in Canada, has retired and has not been replaced or not been redeveloped. So, and then decision processes have become more politicized. So the strategies, I mean, this is an issue that's important. We need to acknowledge politically and institutionally this is a serious problem. And we need to rebuild the Canadian capacity for engineering and managing delivery of large infrastructure developments. And we need to do this in the context of maintaining or ensuring a sustained infrastructure development program. You can't decide you're going to go into this and then get out of it and so on. So there's a whole industry that is built on engineering, construction, and installation. Next slide. This is, in some cases, it's the forgotten sector in the discussion here, but the forest sector is a very major resource sector in Canada and is an important sector in terms of export. It also has a huge potential as carbon sink, probably the dominant carbon sink potential in Canada. And it's not just planting trees, it's also using lumber for buildings, which is long life carbon retention. It has the potential for displacing emissions-intensive building materials, can be used for bioenergy, but we need to address the challenges of improved harvesting and so on.
Sorry, Oskar, for interrupting. We have 19 questions. I would appreciate if you can maybe summarize your findings.
Yep,
thank you.
I'm almost there. So here, okay, next slide. So this is the last one, is the carbon capture, use, and storage. So at the present time, natural gas is likely to assume a major increased role for electricity supply. Western Sedimentary Basin has been proven as a very good storage site for permanent deep sea CO2 sequestrations. So I think the strategies there, first of all, is just acceptance that CCUS is absolutely essential for achieving net zero. There is a lot of engineering and research activity that's required, and we need to look at the whole CCUS in a very integrated way. So my last slide is really bringing together the key point here that I want to recognize is that achieving net zero, we are talking about costs that are in the trillions of dollars, and it's very important that we have a planning approach which is integrated with the systematic development of engineering and technological development that ensures that this whole process of planning and engineering is fully integrated. So that is the key message there. So that completes my presentation, Sohail, and I'm sorry I went over a little bit.
Sohail, you're on mute.
I'm sorry. Oskar, was a great presentation. I really enjoyed it, and thank you for doing such a great job. Your work is really appreciated with respect to Trachea report. My questions that I'm kind of bundle a bunch of questions are related to Trachea study that it was done 5 years ago. So first question is, how many of those scenarios are still valid? The second question is, okay, there has been some new technologies, etc. What has been the impact of those? And the third question is, with all of the money that Biden and his administration is planning to spend, what do you think would be the impact on the results of the Trachea report? So, yeah, please go ahead.
Sorry, I'll answer your first question. I didn't hear the second one properly, so let me answer the first question first.
Sure.
I think and your first question was what has happened since the Trachea work that would change the way we would approach that. The main thing that has happened is that there have been a series of technological developments that we would want to bring into the process that we did not bring in at that time because we didn't recognize them as necessarily being viable. The first one of those is carbon capture and storage. We were aware of the Boundary Dam project, but we were not certain that carbon capture and storage was technically viable. We would certainly include that now, and there's no question that it is technically viable. That was one. The second major change was with regard to the use of electricity for heavy freight transport. Okay, because at that time the battery technology didn't exist for heavy freight transport. It does now, and I think there's been some developments in terms of hydrogen fuel cell technology that can be considered for heavy freight transport, including rail transport. So those are really the two biggest developments. I think there's a much greater understanding of the challenges with intermittent renewables, and that really needs to be addressed in a much more thorough way than it has been to date.
So the willingness of many countries, especially the US, to spend huge amount of money on reducing greenhouse gas emissions, would that have any on the outcome of the Trachea study?
Well, I think the strategies, the strategies for Canada and the US are quite similar in terms of the way they have to go about that. The most significant difference is that the United States is starting from a system that has electricity, which is thermal dominated, whereas Canada's system is hydro dominated. And so there's an opportunity for Canada to provide an export opportunity to help the United States move more quickly to decarbonizing their electricity supply system. But it should also be noted that the work that we've been doing on gas with CCS, for example, there's a lot of work going on in the US looking at that same concept.
Okay, thank you. And then there's a quick question with respect to carbon cost to justify CCS. At what carbon price you can justify CCS economically?
Sorry. There's a general question about the cost of CO2. When, what is the right cost for CO2? So I think the work that was done by the Ecofiscal Commission, where they came up with a recommended cost of around $210 per ton. I think it's a credible number. It has to be recognized that the marginal cost of CO2 is in that order, and it will likely go up over time because the solutions down the road are going to be, the marginal solutions down the road are going to be more expensive than the ones in the short term, because we should be looking at the low-hanging fruit at this stage. But the challenges will later come in, when you're dealing with decarbonizing the various industrial sectors. Those are much more complex.
Okay, thanks. So I think we are going to go with the panel discussion and hopefully answer some questions. Eddy, this was a question for you. You mentioned that 30% energy efficiencies is essentially what we have achieved in terms of reduction of greenhouse gas emissions. Using energy efficiencies, the greenhouse gas emissions have been reduced by 30%. So what about the other 70%? What do we really need to reduce that other 70%? That was one of the questions from the audience, and I think I invite both of you to answer it.
So shall I go first?
Sure, please.
Yeah, so I mentioned that countries believe that they can reduce their emissions by 20 to 30% based on conservation and energy efficiency. I think some countries have managed to do that. Iceland would be a very good example of a country that has done that. But there are very few countries, in my opinion, that have taken energy efficiency and conservation seriously enough to have achieved that number. Nevertheless, it's achievable. I think it's achievable, but it really will require some serious behavioral changes in the population before that happens. The other 70% really depends on the country's economy and what fuels that they're using. I think that a lot of it will depend. If you're a non-fossil fuel producing country, that'll be much easier for a country like that to focus on things like hydrogen, things like nuclear. I think we're going to need nuclear energy if we're going to achieve those numbers. And maybe Oskar is correct. If we managed the building of nuclear plants properly, I think we would be in a very different position than we are now. But these are the kinds of things we're going to need. Hydrogen, fuel cells, nuclear, a lot more renewable energy.
And Oskar, would you like to add anything to it?
Well, I think that's a complete answer.
Okay, great, thank you. This was a comment which is very interesting, is about adoption. The same way that we are living up with Corona, why don't we spend some of the money and the strategies on adopting with the negative impact of climate change. Any thoughts on that?
Well, I'm happy to start the answer on that.
Sure.
There's the fundamental difference between tackling the corona virus challenge and the climate change challenge is one of time. The coronavirus is immediate, so you're not dealing with pathways. You're dealing immediately with policies and actions. Okay, when you're dealing with long-term changes, you then have to recognize that there's a whole bunch of things that need to change in the process, and you need the planning which defines the pathways, which should be the basis for informed dialogue between the various people who are involved in the decision process, so that there's a clear understanding of what are your short-term priorities, what are your longer-term priorities, and what are you going to do in which decade, and so on. So the whole philosophy of planning is really very fundamentally different.
Thank you. How about you, Eddy? Any thoughts on
Yeah,
that?
so I heard the word adapting to climate change as well. Is that correct? So
Yeah. Absolutely.
So listen, the first thing that Biden did on his climate change file is put in billions of dollars to adapt to climate change, because he realizes that no matter what the international community does, and there are some countries you can trust that they will do the right thing, but there are many countries in the world that you don't trust. And it's likely that the global temperatures are going to increase over time. And so you have to adapt to climate change. And here in Canada, and so that's what Biden has done almost immediately out of the gate. Here in Canada, we have a carbon price that the government is charging, and it's going to go up to $170. But they haven't thought in a visionary fashion what they're going to do with that money other than give it back. They really need to focus on using those dollars both for mitigation in large-scale projects, as our colleagues at the Bowman Center have talked about, and as well in terms of adapting to climate change, because we're going to have to do that.
Yeah. No, thank you very much. I think we are almost getting to the end of the session. I was going to maybe ask each of you in 1 minute to summarizing your thoughts. We have another 18 questions unanswered, but I think maybe we will do it at next webinar. So Eddy, would you please start with your 1 minute concluding remarks?
Yeah, I think that in the end, the whole issue of net zero and achieving the targets that we as a global community set to ourselves is going to be dependent on trust, and trusting countries that have committed to do it to actually fulfill their obligation, but also starting to build a community that is pushing countries to demonstrate that they can be trusted. I think that's going to be a key. Trust is going to be a key to net zero.
Thank you. How about you, Oskar?
Well, my response is more focused on Canada. We have lost a lot of time from 1990 to 2020, and as Eddy had pointed out, we have a long ways to go. So the challenge to get to net zero by 2030 is even more challenging than it was 5 or 10 years ago. But what is required in getting there is really a fully integrated approach that combines the process of engineering and management and delivery of large infrastructure development with having comprehensive integrated fact-based planning. And these two things have to be going on together and interactively. And this is very, very important because there's a lot of money that's going to be required to achieve net zero. And it really is incumbent on ensuring that that money is spent as wisely as possible.
Thank you very much, Oskar. Well, my sincere appreciation goes to both of you gentlemen for doing such a great job, such an outstanding job. I mean, the reason that we get so many questions is because of the good presentations that you made. And I think moving forward, maybe what we need to do, rather than having 1.5 hours, we will change it maybe to 2 hours or even maybe longer. Also, I want to thank all of you, our participants, for joining us today. I know your active participation has made this a lively and exciting virtual event. I don't know how to thank you. This is great that you are showing so much interest in the whole work. And please keep in touch and can stay tuned. So we are going to come back with maybe longer webinar next time. Have a great afternoon. Thank you.
Thank you too, Sohail. Thank
Thank
you for sharing this.
Thanks.
Thank you.
Thanks.